Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the statements of the second law. As pointed out repeatedly in the former projects, energy is a conserved property, and no process is known to have taken place in violation of the first law. Therefore, it is reasonable to conclude that a process must satisfy the first law to occur. However, satisfying the first law alone does not ensure that the process will actually take place. It is a common experience that a cup of hot coffee left in a cooler room eventually cools off. Now, let's consider the reverse process, the hot coffee getting even hotter in a cooler room as a result of heat transfer from the room air. We all know that this process never takes place. The paddle wheel rotates as the mass force and stirs a fluid within an insulated container. However, the reverse process raises the mass by transferring heat from the fluid to the paddle wheel. Does not occur in nature, although doing so would not violate the first law of thermodynamics. Consider the heating of a room by the passage of electric current through a resistor. Now, let's try to reverse this process. It will come as no surprise that transferring some heat to the wires does not cause an equivalent amount of electric energy to be generated in the wires. This process cannot occur even though they are not in violation of the first law. It is clear from this argument that processes proceed in a certain direction and not in the reverse direction. The first law places no restriction on the direction of a process, but satisfying the first law does not ensure that the process can actually occur. This inadequacy of the first law to identify whether a process can take place is remedied by introducing another general principle, the second law of thermodynamics. A process cannot occur unless it satisfies both the first and the second laws of thermodynamics. The major use of the second law include: the second law may be used to identify the direction of a process. The second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and the transformations of energy from one form to another with no regard to its quality. The second law provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. A second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems such as heat engines and refrigerators, as well as predicting the degree of completion of chemical reactions. Let's talk about the thermal energy reservoir. In the development of the second law of thermodynamics, it is very convenient to have a hypothetical body with a relatively large thermal energy capacity that can supply or absorb finite amounts of heat without undergoing any change in temperature. Such a body is called a thermal energy reservoir, or just a reservoir. A reservoir that supplies energy in the form of heat is called a source, and one that absorbs energy in the form of heat is called a sink. Thermal energy reservoirs are often referred to as heat reservoirs since they supply or absorb energy in the form of heat. In practice, large bodies of water such as oceans, lakes, and rivers, as well as the atmospheric air, can be modeled accurately as thermal energy reservoirs because of their large thermal energy storage capacities, or thermal masses. The typical statements of the second law include: first, Kelvin-Planck statement. We demonstrated earlier for the heat engine that even under ideal conditions, a heat engine must reject some heat to a low temperature reservoir in order to complete the cycle. That is, no heat engine can convert all the heat it receives to useful work. This limitation on the thermal efficiency of heat engines forms the basis for the Kelvin-Planck statement of the second law of thermodynamics. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a neat amount of work. The Kelvin-Planck statement can also be expressed as: no heat engine can have a thermal efficiency of 100%, or as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. The impossibility of having a 100% efficient heat engine is not due to friction or other dissipative effects. It is a limitation that applies to both the idealized and the actual heat engines. A heat engine must exchange heat with a low temperature sink as well as a high temperature source to keep operating. Various statements are equivalent, and violation of one statement must violate other statements. 2. Clausius statement. There are two classical statements of the second law: the Kelvin-Planck statement, which is related to heat engines and discussed in the preceding section, and the Clausius statement, which is related to refrigerators or heat pumps. The Clausius statement is expressed as: it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. It is common knowledge that heat does not, of its own volition, transfer from a cold medium to a warmer one. The closure statement does not imply that a cyclic device that transfers heat from a cold medium to a warmer one is impossible to construct. In fact, this is precisely what a common household refrigerator does. It simply states that a refrigerator cannot operate unless its compressor is driven by an external power source, such as an electric motor. By this way, the net effect on the surroundings involves the consumption of some energy in the form of work, in addition to the transfer of heat from a colder body to a warmer one. That is, it leaves a trace in the surroundings. To date, no experiment has been conducted that contradicts the second law, and this should be taken as sufficient proof of its validity. It simply states that a refrigerator cannot operate unless its compressor is driven by an external power source, such as an electric motor. 3. The increase of entropy principle or actual process in nature always proceed spontaneously and irreversibly in the direction of entropy increase. We have discussed before the increase of entropy principle, and we have mentioned this is one statement of the second law. For an isolated system, the increase of entropy is the entropy production. That is, the increase of entropy for an isolated system is not less than zero. If an irreversible change happens in an isolated system, the entropy change is larger than zero. If a reversible change happens in an isolated system, the entropy change is zero. If the entropy change is less than zero, the change or the process happening in an isolated system is impossible. Okay, that's all for this task. Thank you very much, and see you next time.